Hello and welcome. I would like to present our recent findings related to X-ray induced bone damage during in situ micro-CT experiments. Bone fragility and fractures are a major global health concern due to changes caused by aging and certain medical conditions that occur on the micro scale. This is why Synchrotron micro-CT in situ experiments are used for detailed analysis of bone tissue and the development of advanced fracture computation models. In a typical in situ experiments, like the 3-point bending test, we would apply the external load to the bone sample to initiate the fracture and use micro-CT to acquire detailed images during the loading. However, even without applying the external load, we would still observe the crack development at a longer exposure time, since the radiation itself can damage the bone tissue. And this raises a critical question: how does radiation affect bone fracture during in situ micro-CT experiments? To provide explanation behind the radiation-induced bone damage, we prepare a series of bending tests of cortical ovine bone samples in 2 orientations under no exposure and 4 acquisition time groups during micro-CT imaging. Next, we performed microindentation to assess changes in bone mechanical parameters and Raman spectroscopy to identify compositional changes at the molecular level, along with Monte Carlo simulations to estimate the actual dose deposition. We observed significant reductions in both elasticity and hardness with increasing radiation exposure time. Raman spectroscopy revealed changes in both the mineral and organic phases of bone tissue, and the dose rate results show local and non-uniform dose deposition across the samples. In conclusion, the radiation emitted during Synchrotron micro-CT significantly affects bone properties in a dose-dependent manner. And finally, as a part of future work, we would integrate advanced dose estimations and predictive multiscale modeling. Thank you for your attention and come to see our postdoc.